So this was the program. Hopefully you figured out the program was doing some kind of Monte Carlo thing. So we start out with this S value. S stands for state. So the state is some kind of number. We have these terminal states, and we know that from the hint here that they're terminal states. We have a minimum one, which was -3, and a maximum one, which was +3. And then we run some number of loops, and in each loop we sample one episode. So one episode is one happening of the Markov chain until it gets to a terminal state, until it stops. And then we start simulating each episode. We go until the episode is over, and we just add on coin flips. So we make these coin flips, and we replace the value of S with S plus equals coin flip, so it either goes up by 1 or down by 1. And we keep going until we reach either the minimum or the maximum. If you get to the minimum, then the total return for that episode, the episode return, is the reward at min S. And if you get to the maximum, it's the reward at max S. And someone can decide what these rewards are. We somehow decided they should be 0 and 1. And then we finish the episode, and we go to this important line right at the bottom that says, update the value. So the value plus equals alpha times whatever the total return for the episode was, minus the value. This was exactly the kind of online averaging that we left off with in the last class before the break, of doing averages but in this online way. So it's a kind of a funny thing if you've never seen it before. Hopefully it's jogging a little bit of memory with the constant alpha. So let's see what you guys said about this thing. What should value be, and what should it depend on? All right, and let's see what people said. Okay, I need to probably zoom out a bit. Zoom out, okay. So, out of 17 people who responded, only 7 people think it depends on how large num iters is. That's a little bit less than half. 10 people, a little bit more than half, think it depends on what alpha is. 6 people, which is, again, quite a bit less than half, think it depends on what value was at the beginning. So value is some value at the beginning, and then we're updating it here. And then we have, out of 17 people, we have 9 people that it will be close to, but not equal to 0.5. 6 people think it will be close to some other value, but not 0.5. Nobody fell for my trick that it will be exactly 0.5, so that's very good. This is one thing to remember about these Monte Carlo algorithms. You will never get an exact answer because it's random. It's some kind of random answer, and you can control how close to get by, again, things we talked about last time, but you will never get it exactly. So you should not expect to get it exactly. Nobody fell for that. But it looks like the class is really quite split. I will say, I'll tell you for sure, it depends on at least one of these things. So at least one of these is right. Of course, it's a choose all that apply. So it could be 1 or more, but I'm telling you it's not 0 now. So you don't think it's a trick. It doesn't depend on anything. It depends on at least one. I'll let you revote. You can pick which ones you think it depends on. And of course, one of these 2 things is true. It's going to be either close to 0.5 or it's going to be close to something else. One of those 2 things is true. So I'll let you revote and think about what it is. Yeah, all right. We'll give you a few more minutes. And again, feel free to chat with your neighbors.
Remember the number of iterations to set the precision. So like it does depend.
If it will be close to some other value,
I mean, like,
then it's not dependent on alpha.
obviously
Sorry,
there
but
are
it is
alphas
dependent
where,
on alpha. If it's
but if alpha's properly between 0 and 1, I don't think it matters. Like if alpha's 0 or alpha's
and
negative,
it also shouldn't be dependent on what the value was before.
but we can probably assume alpha's selected.
Alpha discounts stuff that happened like further in the past, right? So
Yeah, because there's no value that has to be alpha. It's just
I can't think of any.
just thinking about
I'm also assuming that these are all relatively reasonable. Yeah. This right. Yeah. I agree.
yeah, I think it's expected that it will. In this case. Characteristically, yeah, but that's the algorithm to move towards. So it's plus equal alpha times the difference between the last one and the mean. And so we'll just get closer and closer to the mean. well, not always closer necessarily, but over time it's supposed to converge. Maybe it doesn't.
Yeah.
It's supposed to be so you keep going, it's almost like an average score.
It depends on the number. Alpha
Right.
and
Yes.
the value will be close to some other value, but
Yeah.
not 2.5. Because the thing about it has to be dependent on numbers, because if numbers is 1,
Yeah.
you're just, it's going to be either 0 or 1. And then when you multiply that by constant alpha, if you start out with a value of 0, you're going to have
Yeah, so
alpha.
if you do it for a finite number of samples, it will always
And
be,
on
there will be
average,
some
you'll-
distribution, and you can
like, it'll
prove
set
that the
the average
distribution is
out
centered
between-
on the real
It should
value.
be exactly.
So in this case, whatever
So
the theoretical
you should
value is, it'll be
times alpha
some,
over 2.
most of the time it's normal distribution around that theoretical value. If you run it for an infinite
You're
number
supposed to go
of
to-
loops, you can
you're
like
supposed to
cook
converge to
things up so
0.5.
that in the limit as the number of iterations goes to infinity, it actually converges to the
I think
So-
that's converged to alpha.
yeah, so in a finite number, you're always some distance away, and then in an infinite number, you can cook it up so that it gets closer and closer to infinity. Yeah. Okay. All right, so put in your final guesses. Let's see what people settled on as the consensus. Okay. Okay. So, out of 17 people, we have a little bit of movement, but not too much. So, people started to think it depends on num iters. It definitely depends on num iters. So, if you selected that, you got it right. This is the kind of thing we saw last time, is that when you run a Monte Carlo algorithm, more iterations will get you closer to the right answer, right? So, and you should always be thinking of the sort of central limit type theorem scaling, where there's something going on with the square root of the number of iterations, right? So if you run 100 times as many iterations, in principle, you can get a 10 times closer answer in some sense. And this is partially why these Monte Carlo algorithms, they can be quite slow, is because like if you want to get a lot of precision, then like if you want to be accurate to within 0.0001, like on your lab, then you're going to have to run, that's 1 over 10,000, you have to run 10,000 squared simulations, which is some huge number. That's 100 million simulations. And that is actually why I make the precision so small in the lab, so you can't like cheat and just do a Monte Carlo and get close enough, right? If you do Monte Carlo, it's quite tricky to get really precise answers because it takes a long time. You got to make the number of iterations really big. So that one is definitely true. So good job to people who selected that. This other one is a little tricky. It definitely does depend on what alpha is. So this is this zany thing. We're not taking the actual average. If we were taking the actual average, then it would only depend on the number of iterations. But we're doing this constant alpha MC, and so it will also depend on alpha. And I think, to me at least, the way I always remember what is this connection between alpha and the number of iterations, I remember the fact that we saw last time. So this was the relationship that we saw last time. If you set alpha, instead of making it a constant, if alpha changes as you go, by alpha equals 1 over number so far. Let's call it n iters so far. So not 1 over the total number of iterations, but if you make it, first you make it 1, then you make it a half, then a third, then a quarter. Then it will output exactly the average. Then value plus equal alpha times return minus value will be exactly the average. And that is a little calculation you can do about averages to just see that instead of averaging up a whole bunch of things, you can take the average of the first 100 things and then just add on the 101st thing with a weight of 1 over 100, and you'll get the same answer. So if you do this kind of thing, you will get exactly the average. And in constant alpha MC, we don't change it as we go. We just make it one fixed value. But if you do 1 over alpha, another way to say this is 1 over alpha is like the number of iterations, or the effective number iterations so far. So if you make alpha 1 over 20, it's somehow in some sense going to be looking at the last 20 things that you're averaging up together. If you make it 1 over 100, it's going to be looking at the last 100 things. That is how the alpha matters. So if you make it really big, then it's going to kind of ignore things that happened long in the past and only look at the last few. If you make it too small, then it will be like some big average that looks at many, many of the last things that happen. So it definitely depends on what alpha is. Questions about that one? I know it's a little slippery with this constant alpha thing. It does seem weird when you first see it. You're like, why would anybody do this? But you'll see as we go later, this is a really common thing. And it's partially because in something like this, it kind of seems silly. But as you go, you will see that in more complicated problems, as you are further into the algorithm, you are doing better and better, and you do want to forget what you did at the beginning. Because when you started, you didn't know much. So you kind of want to forget about the situation where you were dumb and didn't know, and only remember the last few. And that's exactly what this alpha does. We'll see more of that as we go in the course. Yeah?
So is it always the case that alpha is 1 over n iters so far, or does it can it take?
Yeah, I think this is like, yeah, it can be anything, but this is a good way to like imagine it in your head. If someone says alpha equals 0.01, what does that mean? That means you're effectively looking at the average of the last 100 things so far. So this is like a good way to think about it. This isn't like, I guess this is not a math statement. This is like a thinking about statement. This is me thinking about it. Yeah, that's a good point. So otherwise it's kind of abstract. Like what does 0.01 mean? I don't know. But 1 over 0.01, 100, I can imagine that in my head. And you can help, this is a good thing to know when you're like diagnosing issues. You're like, well, something weird happened. Like, did I just get unlucky and I like something weird happened in the simulation? Oh, well, that happened 1,000 iterations ago, so it shouldn't matter because I only see the last 100. So that's the right kind of idea. And in fact, you can prove some kind of like exponential thing. There's something to do with an e to the alpha. Your memory of an iteration k iterations ago is something like is like e to the alpha times k. So to figure out how far in the past, or minus alpha times k. So if something was 10 iterations ago and alpha is 1 over 100, then you'll remember it quite a lot because e to the minus 0.1 is like a pretty big number. But if something is 100 iterations ago and alpha is 1/10, then that's like e to the minus 10. You barely remember that. Yeah.
Is that the memoryless property of an exponential distribution, or is that?
This is like the exponential property of the equation. Like the equation we're doing, this equation is very similar to the differential equation f prime of x equals alpha times like v, or return, I'll call it return minus f, which exponentially goes down to the value of the return with a constant of alpha. So it's not the memoryless distribution, it's like the property of the differential equation. And really what we're doing is some kind of discrete approximation to this differential equation. Yeah, okay, if you haven't taken differential equations, don't worry. This intuition is less helpful than not. But if you love this equation like I do, then it's very helpful. Okay. Yeah, great question. Anybody else? Okay. All right. On the other hand, most people said it does not depend, or just under half the people said it does depend. Just over half the people says it does not depend. And I want to reveal the answer now. Reveal. It does depend on the initial value. It is true, there is something funny here. It does depend on the initial value, but the dependence goes down the further you go. So at any finite time, it will always depend on how much, what happened initially, but the longer you go, the more it forgets the initial value. And in fact, we have the equation for it. How much does it remember is right here. K iterations ago, it depends like e to the minus alpha k. So what it was initially, that was n iters ago. So how much does it depend on the initial value of the value? The answer is e to the minus alpha n iters in some sense. So this is how much it remembers the original thing. So if n iters is very large, or alpha is very large, then it basically forgets entirely. Like this number is so tiny, it might as well be 0, and then it completely forgets. You can think of it as completely forgetting the value of value, but theoretically it does always depend on value. And in particular, if number of iterations is low, or alpha is low, then it remembers a lot of where it started. And all of these things, I think it's nice to visualize. So let me run the code and visualize it for you. So here is here is the code. Oh, I guess we haven't talked about what this process is yet. Okay, we'll visualize it in 1 second. You'll see all the things, but I think it's kind of hard to understand what it's doing unless you know what this system is. This is a simple random walk. This is like the gambler's problem, starting at position 0, and you have barriers at +3 and -3. And in fact, we saw this one last time in a nice video. It was this one, which I'll play again until we get to the example.
We'll be looking at a Markov reward process with 7
So here it is. It's this one.
2 of which are terminal. All rewards are 0 except when transitioning to the upper terminal state, in which case it's 1.
So he's going to
Also,
simulate it in a second.
no discounting. The initial state will be the center, and each transition is a 50-50 chance of going up or down. So one episode looks like this.
So you bounce around, and either you
And
hit
another.
the bottom, or you hit the top, or you hit
get
the
it.
bottom again. Okay.
Now to apply constant alpha
Okay.
and
So this is exactly what I wrote. Is exactly the simulation. There's a terminal state at +3. There's a terminal state at -3. You start at 0. You bounce up and down according to coin flips. And the question is, do you end at the top and get a reward of 1, or do you end at the bottom and you get sent home by the police and get a reward of 0? So it's exactly the drunkard's walk from many weeks ago. Okay, so that's what it is. Now you'll see what it is. The reason I'm showing you this is because I'm not going to simulate this. I'm going to simulate the value function and how it goes. Actually, why don't I let Dwayne here
MC, we start by declaring,
show you first,
based
and
on
then I'll show you
nothing,
mine.
that alpha is 0.05. Next, we need to create our VS table, which we can picture like this.
Okay.
These
so,
are the states, and the vertical axis.
So this is important. I only did it for S0, right? I only figured out the value. That's why value was one number. I said I'm always starting at 0. In this picture, it's a plot. We're going to figure out the value at 0, the value at 1, the value at 2, the value at -1, and the value at -2. So we're doing 5 calculations in one. We're not just doing one calculation. But of course, what I did, that was the value at 0. You could equally well make the value at 1, 2, -1, and -2. Okay, but let's see what it looks like.
Axis
And
will
then
tell
I'll
us
run
the
my code as
table
well.
values. The algorithm starts by initializing all non-terminal state values to 1/2, though you can pick anything. In this case, it turns out you can interpret the values as probabilities, so 1/2 is a natural choice. Okay, now we sample one trajectory and apply our update rule. Okay, now if we sampled another episode, we'd get another update to the state values. And as you can imagine, the complete algorithm involves many updates over many episodes. In the end, it just bounces around the true values. So this approach works, but let's measure it. Let's look at the distance between our estimates and the true value and create a new plot. The horizontal axis will be the number of episodes we've processed, and the vertical axis will be the absolute difference averaged across the states. Now, I'll show you how things evolve with an alpha of 0.02, and if we process 30 episodes per second. This shows us how long convergence takes and provides another view of alpha. If we set it to 0.03, we'll see this. We more quickly get to an appropriate answer, but it bounces around more once we're there. If we set it to 0.01, we'll be slow to arrive at our answer, but it'll be a better estimate once we're there. This is just another view of alpha's quick and noisy versus slow and accurate trade-off.
Okay, so I think this is a great plot. We can make a version of this too in our code, but the initial value that you set, right, you chose some guess for value at the beginning of the code. Of course, you had no idea what the true answer of value was, so you put in some random number. In this case, they put in 0.5, which was off by 0.2, I guess at the state S2. But whatever you start with, you're not going to have the correct answer. You're going to be off by some amount. And that is plotted here in the absolute difference as the value at time 0, right? And as you go on, as you run more and more iterations, that's on the x-axis, you're going to get closer and closer to the true answer. And it really is like a differential equation that is getting closer to 0 at the rate e to the minus alpha. And so if alpha is very big, you go kind of quickly. If alpha is small, then it takes you longer to get there. And the difference is that once you get to sort of a steady state, you're kind of bouncing up and down around depending on the size of alpha. So big alphas will bounce around more, small alphas will bounce around less, but you can kind of see what's going on. So this is a much nicer illustration than what I can do in the Colab, but I'll show you that one in a second too, so you can see the actual code in case you have some investigating you want to do. But any questions at this level? This is kind of a repeat from like 2 weeks ago, but yeah.
If we set our initial VS to 0, would it not matter over a bunch more iterations, I guess?
This is okay, you want to set the initial value to 0, or you want to set
He set it to 0.5, which I know it makes sense. I'm in the other one, but if it were to be set to like 0 or 1, like over time, would it converge back?
Yes, yeah, absolutely. Yeah, you can set it to anything you want, and it will always converge back. What happens when you set it to anything you want, you are changing the starting point on this graph. So you should always think as there is some graph of like error versus time. If I was really lucky and the value I initialized value to happened to be the exact right answer, then I would start like 0, and I'd be like really happy. I'd be like, yeah, great, okay, it's bouncing around 0, I got really small error. In real life, of course, you don't know the answer when you start, so you can set it to anything you want. If you're close, so he has set it to 0.5 and the true answer was 0.7 or something, then you start at an error of 0.2. If you like put in like 100 because you're like a maniac and you're like, I think the value is 100, then you're going to be very far away at the beginning, but it's an exponential graph. You'll quickly converge down to this kind of picture anyway. So having the initial value, you should think of it as the initial value in the size of your error, and it can be anything. Yeah. Great question. Anyone else? Yeah.
Just going back to the alpha differences.
Right.
I guess the different alphas that we use. So going back to what you said earlier about conceptually thinking about it, it's like, oh, it's only taking the memory of the, like if it's 0.1,
Right.
so they only take the memory of 100
Right.
versus 200 versus 300.
That's right.
Can you explain to me why the, like, so it looks like the variance of the changes between, why is that the case?
Yeah, so I think the best way to think about it is in terms of this relationship to the differential equation. So this update rule for the value function is very much like the differential equation whose derivative is alpha times this difference. And okay, you can do a change of variables. If that's the value for value, let's look at the differential equation for the function, which is, let's call it E for error. E already means something in math. Okay, let's not write E for error. Let's write delta, that's cool. Okay, delta of x. Let's let it be the value minus the true value. So by value, I mean our estimated value. Minus the true value. As a function, x equals number of iterations so far. Iters so far. And this is like literally this idea delta. That's exactly what is plotted in the plot over here. It's literally delta versus x. So it's not an actual function of a real value x. It's actually it's like a discrete function. But in some zooming out, you can pretend it's a function of the number of iterations x. And that thing will satisfy the differential equation, which is delta prime of x will be alpha times delta of x. With a minus? Yeah, with a minus. So this is the solution to this equation is delta of x is whatever it was at time 0 times e to the minus alpha x. And this is like, I think this is the best way to think about it. Okay, I should say, okay, this is a curve that is going to 0 very smoothly. Why does it bounce around? It's because there's also randomness built on top. So sort of on average, it's going to go to 0 according to this, but there's also some randomness built on top, which is why you see these spiky curves. But on average, it goes like this exponential graph. And so the bigger alpha is, the sort of faster it goes down to 0. The bigger alpha is, the more randomness you also have tacked on, which is why they kind of spread out as well. So there's two competing sort of factors. But this is the reason, the memory part. I think this is a good way to understand it. I'm going to say this is on average. So let's make this let's make delta the average of this. And then everything I say will be completely correct. The average. Okay. Yeah, I'm not sure. Did I help explain it or still?
No, that explains
Okay.
more or less.
Yeah.
So again, going back to that, so because our averages are like random.
Mm-hmm.
Even though it converges to some value.
Yeah.
It's not like it's like, is it fair to say like, oh, like any one of those values are like appropriate answers to what the value should be?
Yeah, so I think the right thing to say is on average it converges to 0, but there is some sort of like distribution.
Yeah.
And so it would be even more accurate to say it converges to some distribution. And that distribution can be either wider or more narrow. If it's more wide, then that means you're getting answers that are not super close to the real answer. If it's more narrow, then you're getting answers that are always very close to the actual answer. And I guess what I'm trying to convince you guys is that how good it is depends on all these things. It depends on alpha, it depends on how long you ran it, it depends on your initial guess, right? Because if your initial guess is way off, then it's going to take you longer to get to 0. All of these things matter, and you should kind of like be aware of them. Yeah, so it's true, if you like really want to analyze like theoretically, it's quite a bit complicated. So on average it's going to 0, but then there's this like noise component on top. And in practice what you do is you kind of like run it and you like kind of watch it over time. Is it converging or not? And like how narrow is it getting? And if it's kind of settling around one value, then you can be pretty confident that that works well. Yeah. Okay, yeah, great questions. Anyone else? Okay, so let's see my version of this code. And again, it's the one that you guys saw this morning. Okay, well this is the one we're going to do in a second with cool arrows. But before we get that, we're going to do this one. Okay, so here I ran the number of iterations, and I have my initial guess, which was 0. In their video, they made the initial guess 0.5. But of course, if you make the initial guess 0.5, in the problem I gave you, which was starting exactly at the initial state 0, and a -3 and a +3, the actual answer is 0.5. And you can see that by symmetry, right? If you start halfway between a -3 and a +3, then what is the chance of going to -3 or +3? Well, they have to be equal by symmetry, right? You're equally likely to go up or go down. So of course, the value at the end will be the average of 0.0 and 1.0, which is 0.5. So I have an initial guess of 0, and then I have this min and max. And if you run it, you get this value of value, and it says it doesn't know what numpy is. Okay, let's try again. And you run it, and you will get a value of 0.36, which is not great. So how could we improve it? We can either run more iterations or change the value of alpha. Right now, alpha is 0.05, so it's kind of only looking at the last 20. Why don't I make it a little bit smaller and see what happens? 0.02, that's like looking at the last 50. The characteristic length is 50, and that should be a little bit better. It's still 0.35. I wonder why it's doing this. Okay, well, let's run it again. Maybe I just got unlucky. Okay, there we go, 0.53. Okay, and again, it's that's what we actually care about, is the value of value at the end of the algorithm. It is instructive to see how it is evolving through the algorithm. That's what was plotted before. So let's add a little bit of code here to do that. Of course, all of this code is just extra fluff. I'm going to add in something called value history, and I'm going to make this an array of number of iterations. And I'm just going to write down what happened as we went. So we only care about value. Value history is just for our understanding, to help us understand. I guess it needs to be zeros. So it actually makes the array. And then I'm just going to write down as we go. Instead of just updating value, I'm going to make value history of iter. Is it called iter? Iter. I'm going to make that equal to value. And then instead of printing value, I can also plot value history. And this will give us exactly the kind of plot we were looking at before. Of course, before he was looking at a plot of the difference. I'm only plotting value. So you'll see what it gets closer and closer to as you go. Okay, hopefully this works. Doesn't know what plot is. Okay. Plot dot plot, I guess, plot. Okay, so there's the plot. And, okay, I guess let me start at the beginning. Let me start at value equals 0 and really make it go. Okay, so there's the initial value was 0, and then over time, the values went up and down, but they are getting closer and closer to the value of 0.5. And now you can actually see why I had pretty bad guesses for value initially. I haven't given it enough time to get to the sort of the steady state is at 0.5. That's not even on my axis. So the reason I'm sucking is because you can think of it in a number of different ways. You can say I started too far away. Like my initial value guess was way too far. You could also say my alpha value is not big enough. If I make my alpha value bigger, I will also get there faster. So let's make alpha a little bit bigger. What was it? 0.05. That'll be a little bigger. And that should move a little more quickly. So in this one, because alpha was a little bigger, I moved more quickly and I got to this steady state around 0.5, and now I'm bouncing up and down around 0.5. So you can hopefully see I got a better guess. Although in this case, I kind of got unlucky near the end and it went down a bit. One thing that is quite common is people use schedules for alpha. So they make alpha bigger at first and then smaller. That's also a common thing. This is also sometimes related to the idea of a learning rate. Alpha is like how big of a step size you're taking. You take bigger steps at the beginning where you don't know anything. You take smaller steps at the end when you think you have a better eyeball on the answer. Yeah?
With an alpha value of 0.05, you're looking at 20 entries.
That's right.
Does that mean that on average your guess doesn't improve at all after you've done 20 iterations?
20 is like the length scale. So like things that are 20 iterations ago count with like an e to the minus 1. Things that are 40 iterations ago count with like an e to the minus 2. So after exactly 20 iterations, it's not that you've completely forgotten everything that came before, but that's like the right length scale in which you start to forget things. Yeah, and it is true in the steady state, if we ran this forever and ever, then you would see that only the last 20 sort of matter. Because if you run it forever, there's sort of some like steady state thing, and it reaches some distribution that it gets close to, and then only the last 20 will matter, sort of starting from that special distribution. But if you start at some actual value, like in real life, then those things will still matter. And in this case, since I ran 100, the initial value counts with like an e to the minus 5, which is pretty small. So I've sort of mostly forgotten my initial value. Yeah?
Is it like saying after the first one iteration, it has a new starting point?
Yeah, you can think of it that way, right? Yeah, because of course this algorithm you can say at time 60 there was some value. Pretend that's the new starting point and run it for another 40. And this is another big advantage of this thing, is if you're running your code, you have like some robot that you're training, and you're like, oh wait, we have this smarter way to train it. You can take what you had before and use that as the starting guess of your next thing, and the closer you are at the starting guess, the better your results will be. So you can sort of import old information in a smart way. Yeah, great, these are fantastic. Okay. Any other questions or comments? Okay, so now you've seen this algorithm to death. Let me show you the picture of this algorithm from the textbook so that you can see it. So this is called Monte Carlo evaluation. And why is it called evaluation? Because we're given some policy. There were no actions, right? The actions were pre-chosen for us. So given some policy pi, in what I did, the policy pi was you go up half the time, you go down half the time. There were no actions, they were already chosen for you. And then you are finding the value of the value function v of s. In the code I did, I only found the value at one point to simplify things a little bit and make it really crystal clear to understand. But of course, instead of having just one value function, you can have value, which is a vector, for every possible state, and you update it at every possible state in the same way that I did before. And what is the algorithm? This is exactly the algorithm you saw. Loop over the number of times you're going to do episodes. Here in the textbook, they chose to do it forever, which is a little bit longer than I'm willing to wait. But then for each time, they generate an episode, and they go until some final time t. Then they add up the total returns, which is this, what they call g. G is the letter they use for the total return. In my problem, there was only prizes at the end, so the total return was very easy to solve, whatever you have at the end. Of course, this is the nice thing about these algorithms, is they're very easy to update. So if you wanted to add something like total return plus equal reward we got now, then it works totally fine. So you can add up rewards as you go if you want to. And of course, it's no problem. And then what they do is they look at all the states that were visited. So in my particular problem, I always started at 0. And so I knew that I was always taking s0 equals 0. In this algorithm, you look at everything you visited along the way, and you look at the first time it was visited, and then you update this average. And here they're doing it not with the constant alpha, but with an honest average. So v becomes the average of all the returns that you saw going through the state s0. So every time you visit some state, you keep track of those visits, and then you average the returns that you got. Okay, so all of this is you're given some policy pi, and you're calculating the value function through randomness. All right, we're going to move on. It's going to get slightly more complicated because we're going to start learning how can we improve the policy pi. But this is a great place It's all going to build on this. So if any part of this is unclear, let me know now. I can try to help. Yeah.
Can you explain again what's going on with the last, the loop for each step of episode, that stuff?
Yeah, okay. So this stuff is here only because they, instead of running it just for one state at a time, they are trying to take all the samples they've done and update all the states that were visited. So in what I ran in this like very simple one, I said, we're always going to start at the initial state. I'm only going to update value, which is a number, at the initial state. But in this code, they are reusing their work, and they're saying, let's make value a vector, and we're going to update all of the states that were visited on the way. And so what this code does is it loops through all the steps, and it says, find the states that you visited. That's essentially what it does. You have to be a little careful because you don't want to update one state more than once. Like if you loop in one state like 10 times, you only want to update it once. So you go by the first time you visited a state. So this loop is going through all the possible states that we visited and updating the value function at those states. So that's what it's doing. It's exactly what we were doing just for one state, but they're doing it for many states all at once. Yeah, hopefully, yeah, I know I didn't like fully explain this. If you want to go read the textbook, they have some more examples. But I think it's kind of this kind of like bookkeeping is like a little fluff on top of the core idea, which I really want you to get. Yeah.
So, okay, I see at the top there's a policy pi. That's what's
That's right.
determining the actions.
Correct.
Okay.
Yes. So yeah. So and again, the reason I taught you guys Markov chains before we learned Markov decision processes, which are the things we actually care about. Once you have chosen the policy pi, a Markov decision process just becomes a Markov chain. So you should just think it's something. It's bouncing around. It's moving according to some randomness. That randomness was technically, somebody chose the actions for us. But you can imagine it's just something moving around, and we're evaluating the value function. Yeah.
To go back to that second loop, is it
Yes.
is it like not loop forever, the one after
This one,
yeah,
yes.
Yeah.
Yeah.
Is it like saying in your code,
Yeah.
instead of having one initial state that we always start at, is it like let's say you have a vector of like
Right.
states that you always iterate through
Yeah.
every episode where you still go through all of
Yeah.
the states after?
So yeah, so what it is we have a vector for all the possible states, and instead of updating just one state, I'm going to update every single state that was visited on the way.
Yeah.
So if I passed through state 3 at some point in my path, I'm going to update state 3. And so this loop is what it's doing. It's going through all the times that I were there, and it says if st, if it already appeared, don't update it. We only update each state once. But if it appeared for the first time, then update it. So it's kind of looping through the trajectory. Actually, I think I have literally this code written in the next example we're going to do. So you'll get a chance to see it there too. But it's doing a search through this whole list of things that happened. And it's saying, find all the states that we visited, update those states. Yeah, okay. I'll make sure when we go through the next code, I'll make sure to show you guys this and how it works. Yeah, great questions. Okay, so we're going to move on to the next example. And this is a really common example in machine learning and reinforcement learning. And it is called Gridworld. And I'm going to go up to the very top. So here's a screenshot of the Gridworld from the textbook. So this is the 4x4 Gridworld. Let's see if I can make a little bit more room. So this is example 4x1. And you have to understand what a Gridworld is. So in the textbook, they give you this extremely dry definition. They say, this is a Markov decision process where there are states 1 to 14. Those are the states. And there are 4 actions possible at each state. There's up, down, right, left, which deterministically cause the corresponding state transitions, except the actions that would take the agent off the grid, in fact, leave the state unchanged. So this is a really mathematical way to think about it. The better way to think about it is you're doing a Roomba or a robot. Okay? So this is how I think about Gridworld. You should imagine that you have like a little Roomba. This is like a map of your room, and the Roomba is going down on this grid, and the Roomba is going to try to like move around, okay? And it's really important. I think this is like actually extremely important to understand what the Roomba knows and what it doesn't know. Because the Roomba is trying to learn something, so of course it doesn't know everything to start with, but it does have really good knowledge about certain things. And one thing in particular that it knows is it knows which square it is in with like 100% accuracy. And by which square it's in, I mean it knows the square number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, it knows for sure. So this I think I put as the first bullet point. You know exactly which square you are in, but you don't know which squares are close to each other's squares or anything like that. So you have no knowledge of this like two-dimensional map. This two-dimensional map is something like humans know, but the robot just knows numbers 1 to 14. It has no idea what's close to what. So really, from the robot's point of view, it really should be like a one-dimensional thing. Am I in state 1? Am I in state 2? And so on. It doesn't know what is connected to what. Nevertheless, the robot can decide to take actions. So it can choose the action up, and then it's going to go up. It's going to choose the action down, right, or left. And again, it has no idea what's connected to what. So if it's in state 10, we can see as humans that if it chooses to go up from state 10, it will end up in state 6. But the robot has no idea. So it says, I'm in state 10. I chose to go up, and like, okay, I guess we're in state 6 now. Like, I don't know how we got here. Like, I was in 10, I chose to go up, and I ended up there. So that is, I think, really important to know. It doesn't know what is connected to what. It has no idea about this two-dimensional feature. It just knows about state, which is a number, and action, which is up, down, left, or right. And the other rule that is important to know, if you're on the edge, you can sometimes just end up where you are. So if you're in state 7, and you say, I'm going to go right, and then, oh, you ended up in state 7 again, you happen to not move, right? So that's the rule for edges. Okay. And here it's telling us what's going on. Okay, somewhere it should say the rewards are -1. Yeah, the reward is -1 on all transitions until the terminal state is reached. So there's these two terminal states, here and here. And if the Roomba gets there, then it's over. We stop playing the game. Everywhere else, no matter where the Roomba is, in every step, the Roomba gets a reward of -1. You should think about this. The Roomba is going around here, and you are standing above the Roomba with a big rolled up newspaper, and then every time the Roomba moves somewhere that's not the terminal state, you go, bad Roomba, you hit it. You just hit it over and over. And the idea is the Roomba is going to learn that please go over here, because then I'll stop hitting you with the newspaper, right? So it's always getting a reward of -1. This is, of course, exactly what we did in the very first class, where we said, you're playing snakes and ladders, how many turns until you get to the end? And I said, don't think about the number of turns. Think about the reward of -1 every time you step. It's exactly the same thing. So your total reward is negative how many steps it took until you left. And since you're trying to maximize reward, you're trying to get away as soon as possible, right? That's how we motivate the Roomba to do what we want it to do. We give it bad rewards until it does what we want. Okay, so let me see. Do I have everything else? Okay. So your goal is to kind of learn what actions you should choose to get to where you want to go. So some kind of like map of what actions you should take to go where. And you specifically want to learn to exit as soon as possible, no matter where you're dropped. So ideally, at the end of the day, we're going to have a Roomba. If everything works perfectly well, we're going to throw it somewhere randomly, and it's going to like immediately scurry to the nearest exit, right? So it's going to like, we throw it on here, it's like zoop. We throw it over here, it like goes straight up. That's what you want at the end of the day. Let me see. Okay, I'm gonna talk about the next thing in a second, but is the sort of setup for Gridworld vaguely clear? Any questions or comments? So this is a very general environment. When you read papers on reinforcement learning, it's very often they say, we're going to test our program on this Gridworld example, and they have some complicated thing with many things, or like a maze, or like first the Roomba has to pick up these cherries on the way to like get to the target, or like sometimes there's a cliff, and we're like, the Roomba wants to go from here to here, but if it falls off the cliff, then it loses 1,000 points. So all sorts of variations on this appear. In the literature, we're going to start with this simple example. Okay, I'm going to add one thing here that I think makes it a little more exciting, and appears in a lot of these examples, which is I'm going to make the Roomba is not a perfect robot. So when the Roomba tries to go up, yes, it's trying to go up, but maybe its wheels don't work correctly or something. And so I'm going to say there's a random wind where when it tries to move, there's a 10% chance it moves randomly. So even if it tries to go up, if it's in state 10 and it tries to go up, it will sometimes, 90% of the time it'll go state 6, but it will sometimes end up in 9, 11, or 14 as if it had gone a different direction. And you can think about this as like an unreliable robot. Its wheels, 10% of the time, they break and they go somewhere random, or you can think of it as a random wind. So that's how I'm gonna set it up. Okay, and I'm gonna walk you through the code pretty quickly, because the code that sets up the rules for this thing don't matter. What really matters is, as long as you have this notion of this action, like given a state and an action, you end up somewhere, then you can write all of this Monte Carlo stuff without having to know the details. And this is the beauty of the Monte Carlo. It's not like value iteration where you have to know what to put in the matrix. You can just run it many times given the sort of outputs of this thing. Okay, so that's what we're going to do. Okay, any questions? Yeah.
Just about the algorithm you just showed, but it kind of applies to this. When you update multiple states at
Yeah.
once for a run through,
Yeah.
they all end up getting updated by the same thing because you go through the same rewards. Or I guess it depends on if there are ongoing rewards.
Yeah, that's right.
Surprise.
So if there was a terminal reward, then they all do get updated by the same thing. If there's ongoing rewards, like there are here, where it gets a -1 at every state, you look at everything that happened after you pass through there, and it's like you can think of it as a whole new simulation with just that.
Got it.
You will see this exactly when we do it. So the first thing we're going to do is just repeat everything we did for this thing. Okay, so let me run the code. Okay, and here is the setup of how this is implemented in the code, and none of this is really important. So like I have state 0 are the terminal states, and I have right, up, left, and down are 0, 1, 2, 3, but that is not going to matter. And there's some definition, but the important thing is that we know that there's this function called Gridworld next state that just inputs the state and the action, and it'll tell you the next state. So I'm in state 10, I chose to go up. Where did you end up? I ended up in state 11. And in real life, you don't have a function like this. You have a robot, and the robot is like, I'm in state 10 right now. I drove my wheels this way. Where am I now? I'm in state 12. So, of course, this is all simulated in the code with some kind of like random.choice, the wind, some cosines and sines, and it involves these arrays that somehow encode what is connected to what, the x coordinates and the y coordinates, but none of that matters. You can think of this Gridworld next state as some kind of black box. You're in some state, you chose some action, you ended up somewhere. Okay, all right. And I have the definition is terminal, just so that the Roomba will say, oh, I made it to where I want to go or not, right? So very nice. And I have a function called visualize that lets us see it. So here is the first visualization. These are all the states and their numbers. So this is state 0, state 1, 2, 3, 4, 5, 6, and so on. And this is terminal of state. So you can see most of the states are not terminal. This state and this state are both terminal states. Okay, and now I'm going to apply the algorithm we had before, Monte Carlo value function for a given policy. And this is exactly the pseudocode we just saw in its full detail. So you tell me the policy. What is a policy here? A policy means at every square, you tell me to go left, right, up, or down. And given the policy, I can run some number of episodes, and I will return back this average that we just did. So it's literally doing this algorithm over here. There's one other input to the thing, which is the maximum time. Why do I have to include a maximum time? Because the Roomba sometimes will do stupid things, like it'll get stuck here trying to always move into the wall forever. And if I didn't have a maximum time, the Roomba would just get stuck in an infinite loop and the algorithm would never finish. So after 200 times of hitting the Roomba over the head with the newspaper, I say, okay, you've had enough, and I just turn it off, and we start over. Okay, but it does exactly the algorithm before. And so this is the thing you saw before. So this is the big loop on the outside going over the number of iterations. Then it generates the history of observation. So it starts in a random spot. So we drop the Roomba down somewhere randomly. That's like the initialization. And then we create one episode of history. Like before, I write them down in some matrix. So I have a history of all the states I saw, a history of all the rewards I saw, which start out with nothing. And then this while true is looping until we're done. Okay? So I write down the current state. If we're in a terminal state, I stop. And that's what this break does. That's very similar to what before I give it a name, like, is the episode over? You just have to know that it's a break. If we're not done, then I hit the Roomba on the head with the paper towel or newspaper. So I give it a reward of -1. And then I keep going and I keep going. And I update the state using the function Gridworld next state. So you can see the details of how this function works. Something about like the matrix M, none of that is there. The only thing you need to know is this function that takes you from the state you're in to and what you chose to do. Policy of current state is your action, and takes you to the next state. And I add one to the time, and I just keep going and going, either until we reach a terminal state or we exceed the maximum number of time. And then at the end, okay, so this is exactly this like the kind of code we had in the warm-up problem. At the end, we do the update. And this is update the value function for the states we saw in this episode using this first visit rule. And this is the loop that is being done over here that you guys wanted to see. This loop over here. So what it does is I write down all the things that I've visited already. And I start out with nothing. And I loop through all the times from 0 to the final time. And if I find a state that I haven't visited yet, then I update that state. So I'm going through all the history of all the things that I did. That's in state history of t. And I update all the things that I see. G is exactly the total return, right? It's the sum from time t to the final time. And I write down how many times I visited it. This one, it's not doing a constant alpha. It's doing an alpha with 1 over the number of times it's been visited, which will be exactly the average. But here's the formula, and it looks exactly like before. It's G minus the value function at the state times the weight. If the weight was a constant alpha, it would be the constant alpha MC. And then I mark that state as visited, so I don't accidentally update it more than once. OK. So what do you get at the end of the day? You get something like this. So here is an example. Did I forget to run something? Yes, you have to run the code, not just explain it. OK. OK, so here is a picture with evaluating a policy. So this is the policy called always move right. This is the policy. No matter where you are, these arrows show you what you're doing. You choose to always move right. And I ran this Monte Carlo thing. So I dropped the Roomba down. I let it follow this policy. And I saw how long it took until it reached different states. And I came up with these value things. You can see if you start in a terminal state over here, great, you're done. You're immediately finished. Your reward was 0. You finished right away. You got hit on the head 0 times. Very nice. Same with if you start over here. If you start over here in the always go right policy, then your reward is like -4 roughly. And that's because most of the time you'll take 4 steps and get to there. I guess that's only 3 steps? Maybe -3. 1, 2, 3. Let's read. We can read on the vector. Okay, it's like negative some amount of number. However, it's actually a little bit worse than -3. You get hit, on average, you get hit on the head with a newspaper more than -3 times from here. Does anyone know why it's more than -3? Yeah.
Is it because you might go up anyway?
Yes, right. So the Roomba, of course, is trying to go right, but every now and then the random wind happens or it slips and it goes up, and then now it's going to be in for a long ride and get hit on the head a lot of times. So the average is around -3. That's -3 is like the most likely thing to happen, but of course things can get worse, as they always can, and so it can get hit on the head a lot more times. And in fact, if you start here, you might think the Roomba would just be stuck here forever, but actually it only gets hit on the head about 120 times before it finds its way out. And that's because even though it's trying to just go right, if it gets lucky and the random wind happens 3 times, it will eventually make it over here. So even though I said you can go up to time 200, on average it takes about 120 steps to reach from here to here. Okay, that's the policy, always go right, which is kind of a silly policy, but I think you can see what's going on. A more exciting policy, here is a random policy. So the Roomba comes out of the factory and is like, I don't know what I'm going to do at every state. Let's pick randomly. Here's a random policy. Okay, so this is a more exciting one. And you can see, just by random chance, these two are pretty good, right? If you're here or here, then you're going to quickly go over here. You might notice something a little unusual, which is the policy are these arrows. And you're like, well, why did this one come out green and that one came out yellow? Right? This one says, this is around 0. That's what you'd expect, right? You step this way. This is a pretty good step. I don't understand why this one should be much larger than this one, right? This one says -20. This one says right around -1. And actually, you can read off here. So this one is -1.3, this top one. And this one, I guess, is state 1, 2, 3, 4. 1, 2, 3, 4 is -17. So this one, -1.3. This one, -17. Does anyone know why that would be? Yeah.
Is it random?
Yeah, it's random. So like, how could you fix it? This is like, you look at this, you should say, like maybe we got unlucky. Like this one is actually not much worse. So how would you fix it? Yeah.
Turn up the number of iterations.
Yes. So this is the value. We ran 10 iterations. We had 10 simulations of the Roomba running around. Let's run 100. And you can see if you run 100 iterations, now it's a little bit better. You see that both of them are more similar, right? This one is -7.9, and this one is -4.2. They've become more similar. And again, you shouldn't expect them to be perfectly the same, but they're getting closer and closer. So sometimes that's your problem. When you're doing these Monte Carlo things, you got to always be aware maybe you got unlucky. And if you run more iterations, you can reduce the role of bad luck. Okay, so this is a policy with the arrows, and we've used our update rule. We ran the Roomba around, and everywhere on the path of the Roomba, we update the value function according to that Monte Carlo update. And now we're at the really exciting point where we can ask the question, okay, we have the Roomba, we have this policy which was random, we calculated the value function. How can we find a better policy for the Roomba? How can the Roomba learn from this and improve? Okay, I'm going to let you guys think about it. I have a word cloud where you can put in any of your ideas, and we will take your ideas and use them to improve the Roomba. So let me give you like 2 minutes here, and you'll see it's actually not super complicated.
You just move to whichever adjacent has the highest value. Create a session.
No,
Yeah, I'll put something.
I don't know if this will look in the word cloud.
Okay, so there's like 30 seconds left. Feel free to put in whatever you come up with. We're just brainstorming here, so there are. Put anything you want, and we'll figure out what works after.
It might be separate. No, it's the word cloud.
Okay,
Let's start on
so let's take a look at what people said. Okay, again, we don't want this going. Okay. I want to open this up. Okay. Oh, word cloud. Okay. All right. So, adjacent was apparently quite common. That's a good one. What else we got? I think I can scroll down. Okay, this person put underscores in. Greedy search maximizing R. I'll flip through some of the. So lots of people using the value function. Iteration, probably value iteration. Let's see what people said as things. Actually, 2 people said this first one, which was move to the adjacent tile with the highest value. That's a great idea. Let's keep that one in mind. Take the optimal value. I think take the optimal value is a less specific version of move to the adjacent tile with the highest value. Maybe that's what they meant. Same with this idea of greedy search. Something to do with kind of looking around and picking the highest value. This is great response, by the way. Math, yeah. Roombas are really good at math. Okay. Value iteration. I think I want to point out what we're doing in value iteration. You have access to those matrices M, right? You know if you choose a certain action from a certain spot, you know the probabilities that you're going to do everything. The reason we can't do value iteration is because we don't know the probabilities of anything. Like we don't have access to the matrix that says state 10 is connected to state 12. If we had that, then we could do value iteration. But value iteration somehow deeply depends on that matrix M. We can't do that exactly. So we want to come up with some kind of iteration idea that's not value iteration. That's what we're doing here. Okay. Go to high value adjacent squares. So same idea. Again, move to the neighboring state with the least negative value. So same idea. Again, I think you guys have all figured this out. That is exactly this idea of greedy policy improvement. So I'm going to write this down. This is something we had when we were doing value iteration, it was the same picture, and it's called greedy policy improvement. And it is this picture of, on one side, you have v, which is the value function for some policy, value function pi, given policy pi. And that's what we've done so far. So even if pi is a random policy, we can calculate v pi. And then we can do this thing of we can improve by taking the greedy policy. Let pi equal greedy of v. This is the greedy policy. Let pi. And then once you get the greedy policy, you can recycle again. So you can calculate for the policy you came up with, you can calculate v pi, and then you can do this loop forever and ever. So one side of this loop is called value, finding the value function, or a value approximation. I'm going to say value function evaluation. I think that's the clearest way to say it. And the other way is called policy improvement. And this is one way to do it, is if you have a better value function, you can take the greedy thing. And what is the greedy thing? In our case, it is exactly what you guys all described, which is, from a given spot, what should the policy at this square be? Right now, the policy says go right. But we can improve the policy by, instead of going right, why don't we go to the square that is closest to the end? And closest to the end means the one with the best reward. So instead of going right and getting a reward of like -60, why don't we go up, and then we'll get a reward of like -5. We only get hit on the head 5 times. So from this state, going up is clearly better. And you can see that as a human, that you should go to the one that is the best. That's exactly what we want to do. That's the greedy policy. At every state, just pick whichever is the best. What is the problem with telling the Roomba this? Yeah.
The Roomba doesn't know what's up.
Yeah, that's right. So the Roomba doesn't know that this state and this state are close together. So how are we going to do this? We're just going to, for every possible state, we're going to have the Roomba try all 4 possible actions. And then the Roomba will do the following. It's going to try each action once, and it'll do the greedy policy improvement of trying the 4 things, pick the one that came out the best. And so that's our version of greedy policy improvement. And it's not perfect because we don't actually know that this is connected to this, but in real life, that's what you can do. Of course, we could have written down, we could have had the Roomba as it was going to generate this, we could have had it also write down what actions are you taking, and then it would already know, like, if you're here and you go right, something happens. If you're here and you go up, something happens. So this could be built in already, but we're going to do it the sort of naive way and just do it after the fact. So I have this code, policy improvement, using the greedy policy, and this is the function greedy policy, and it inputs a value function. So this is like the opposite of what we had before. This greedy policy inputs a value function and will output a policy. And a policy, of course, is do you go up, down, left, or right at every possible state. There is also this little variable called number of tries per action, and that we're going to have the Roomba try up, down, left, right from every given state some number of times and see what is the best. Okay? And so here's the code, and I can describe it to you quite quickly. So try every possible state. Start out with your best action being nothing and your best value being -infinity, and try every action. Up, down, left, right are the numbers 0, 1, 2, 3, 4. Try each of them number of tries per action times, and just write down the average of what you get. So you use the Gridworld next state function. So for the state we're in and the action we're trying, just figure out what would happen if you're in that state and you take that action. Average it up over some number of tries, and if the value you got is better than the best possible value, then that's the action we're going to choose. And at the end, we just return all the best actions. So you can imagine the Roomba is here, and it tries going up, it tries going left, it tries going down, it tries going right, and it sees which of those 4 actions is the best. In this case, probably going up will be the best action. And then we get a new policy called the greedy policy. Let's see what this looks like. So here we go. And here is me running it one time. So here is the original policy. So some random policy. It's got all sorts of dumb things in it like this, where of course you get very bad. You get hit on the head a lot of times over here. You're going back and forth. That's the original value function in the policy. I'm going to keep the same value function, and I'm going to show you what the greedy policy looks like. That's here. So this is the improved policy. And now you can see, instead of going back and forth, right, over here, it's better to go that way, because that had a better result. And in fact, all of these, you had a better result going here. And you can see this is pretty good. The Roomba, if it follows this policy, will get to the end quite quickly. What is plotted here is the old value function, so you can see how it was choosing, right? So this was pretty good. That's why these arrows, they always point to sort of the lower situation. We've improved the policy a little bit. This is the magic of computer science, I guess. If you can do something one time, you just put it in a loop, do it again. We can do this again. We can take this as our policy, and this policy is quite a bit better than the old policy. If we run this policy improvement, this greedy improvement on it one more time, it'll get even better. And that's what I've done over here. Iterating things, I did it like 40 times. Let's run it. And okay. So here we are. We started with a random policy. We got hit in the head with the newspaper 70 times. Terrible. But even after just one stage, it's quite a bit better. Now we're only getting hit on the head 20 times, and only at this one spot where we're just going up, up, up. Otherwise, we're getting to the end pretty quickly. After 2 iterations, look at this. We're only getting hit in the head 4 times. And that is actually, this is a perfect solution to the Roomba problem. If you put the Roomba down anywhere, it will find its way to either here or here in the minimum number of steps possible, which could be as large as 4, roughly. Okay, let's keep going and then see what happens. So this is still good, still good, still good, still good. Uh-oh. Now it got worse. Now the Roomba thinks it should go to the right here. Does anyone know what happened? Why did the Roomba go wrong? Okay, I'll let you brainstorm for 1 minute. Everybody think about what happened. Why is it this would seem to be working so well, and then all of a sudden it went from pretty good, almost perfect, to horrible. All right, I'll let you guys all think for 2 minutes, and we'll take this up as the last thing we do today.
Yes.
You know, that's actually maybe
Tried to go down.
right. Doesn't know go down and it's right. Try to concussion. It's scared. It just wants to go home.
Keep setting up in the same spot, no matter where it goes.
I feel yeah, what if they wouldn't do it by every action so that they were all the maximum, let's just
It's
go.
going from down from 7 to 7. It's like if I'm like, if you started looking like that.
It's just magically.
How many
stuck.
iterations? However, when we try to go right, every time it ended up going down to the week. Isn't like
Supposed to
the increase,
thunderstorm.
like the increased
Tomorrow. No.
Well, yes,
time just because
but
the
also
scale, like went right.
today.
No. It's because you can try to go right. So that's why that falls through. Facing down. Yeah,
Oh, yeah.
down is good, but the problem is when I try to go down.
Tried every time it tried to go side up, right,
Right.
and then it tried to go right, it went down.
I was my phone was like about 9 degrees.
Tomorrow. I'm chilling.
Okay, let's take this up because class is almost over. Anybody know what went wrong? Yeah.
How many iterations are you doing for the value?
Oh, this is a great question. Yeah, fantastic. I think I'm doing 100. So that is actually not the problem. So the value functions are being computed quite accurately. Let's check this. I'm doing 100, and because there's only 16 states, and also every time you run a policy, like more than one state gets visited at a time, 100 is pretty good here. So the problem that I had before when I only ran 10, that is not the problem here. The value function estimates are actually quite good. That is a great thought, but not what's happening. Let me go back to the situation where we had this one. So it involves somehow these two things. Yeah. What do you think?
So when we do the number of tries,
Yes.
so every time we try to go right, the wind pushed it down probably, and every time we try to go down, the wind probably pushed it in the wrong place. So it thought right is good, but it's not.
Yes, okay, so you've identified the problem, which is the value function is quite accurate, but when we went to do our greedy policy improvement, how do we do that? Well, the Roomba goes to every state, and it tries all 4 things one time each. And so at this state, it said I'm going to try going up, I'm going to try going left, I'm going to try going right, I'm going to try going, okay, my up, left, and right are messed up. I'm going to try each direction once, and whichever is the best, I will do that. And if at that moment something bad happened, it got unlucky, when it tried to go down, if it didn't actually go down, and when it tried to go right, it did actually go down, then now all of a sudden the Roomba is confused and thinks that going right is better, right? So it tried to go right, and it ended up here just by the random wind, and therefore it says, oh, this is great. Every time I go right, I end up down here. So I will do that from now on. And you can see, because it got unlucky, we got a bad solution. There's a very simple way to fix it. Can anyone think of how you would fix it? Yeah.
Could we just iterate each direction a few more times?
Yes, exactly. So if you change this variable, number of tries per action, so that's in the greedy policy improvement, instead of trying every action exactly one time, let's try it 3 times, okay? So it's still a very small number. And of course, if you actually have a Roomba in a real robot lab, now instead of your Roomba wandering around for an hour, it takes 3 hours. So maybe this actually ruins you, but you'll see that now it's doing pretty good. It still occasionally will screw up, but less often than before. So now it's finding pretty good solutions consistently that lead to the exit in about 3 steps, which is the optimal. Okay, so that is essentially our introduction to Monte Carlo value functions and Monte Carlo improvement. Question over here, quick.
Is each stage an episode?
No, each stage is like one round of this cycle. Each stage is one round of this cycle. So we estimate the value function, that is 100 episodes. And then we improve using our greedy policy search, which again is you can think of it as some number of micro episodes, because we're like running the Roomba in all 4 directions some number of times. And then we do it again, that's another 100 episodes. And each stage is one cycle of this policy improvement.
Does this get added on to like episodic Markov chains or Monte Carlo?
Yeah, so every time we plot this, we are running the thing 100 times, but with the new policy.
Oh, I see.
So we get a new policy, then we run it 100 episodes to calculate the value function. Then we get a new policy, then we run it 100 times, and so on. Yeah.
It's a loop on top of.
That's right. So it's a loop. Yeah. Okay, great. So it's 11:20. We'll stop there. See you guys on Thursday. Don't forget to turn in your lab and put in nice comments to make it easy for me to read. Okay. See you guys next time.